Well, this video is for the second handout on convergent and divergent sequences. And again, this is a lot of this has to do with limits. So let's take a look at some of these even problems here. I'll start with problem 2. We've got a sub n is equal to 4 minus 3 over n. So this has some similarities to some of those problems that we saw in the previous handout where I picked out the piece that had the n in it and then looked at what was happening to that. Okay, so if we look at the 3 over n, as n goes to infinity, right, if we take the limit as n goes to infinity of this thing, this piece is going to go to 0. So then we'll just have 4 minus 0. So the limit there should be 4. Okay, let's see here. Problem 4. Let's see, a sub n is 2 over n factorial. And so on this one, again, if we take the limit as n goes to infinity, this denominator becomes infinitely large, and that sends the fraction itself to 0. Let's see here. Let's look at problem 8. Problem 6 was actually on that quiz from the last section. Let's see, problem 8, we've got a sub n is cube root n over cube root n plus 1. And although this may not look like it, right, these are powers of n. This is n to the 1/3 power, and this is n to the 1/3 power. So we've got the same power of the variable in the numerator and denominator, and so the limit as the variable goes to infinity will be the ratio of the coefficients, which in this case is 1 and 1. Okay. All right, let's see what else. Problem 12 is kind of interesting because it incorporates that expression from problem 6. So let's see, problem 12, we've got 1 plus negative 1 to the n power over n squared. Okay, so let's look at what happens if we take the limit as n goes to infinity for this whole expression. So in the numerator, as n increases, right, this is going to bounce back and forth between positive and negative 1, which means that the numerator is either going to be 0 or it's going to be 2, but it's never going to be anything else. But while that's happening, the denominator is going to go to infinity. And so whether this is 0 or 2 really doesn't make any difference with that denominator going to infinity. The whole fraction will go to 0. All right, let's see here. Problem 14. We've got a sub n ln of square root n over n. Okay. Well, so I think a good way to approach these problems is to analyze what's happening in the numerator versus the denominator. We have other tools I'll talk about in a minute. But, you know, for example, where we have those situations where we've got something like n squared over e to the n power, this denominator is going to go to infinity much faster than the numerator, and so the limit here would be 0. And that, I believe, is what's going to happen here, right? The logarithm of a number is always going to be smaller than the number itself, okay? And so that means that says that the denominator should be getting larger faster, particularly if we're taking the logarithm of the square root rather than the number itself. I think this denominator will overwhelm that numerator and should make the limit equal to 0. Okay? So there's a reasoning-based approach to this, examining, you know, how quickly are the numerator and denominator getting large. Now the other thing you can do here is, if you remember, we talked a little bit about L'Hopital's rule at the end of last term, and so you can take the derivatives of the numerator and denominator and look at that limit and see what that is going to be, okay? So if we take the derivative, well, let's call this n to the 0.5. So the derivative here would be 1 over n to the 0.5 times 0.5 n to the minus 0.5. So that minus 0.5 is going to put this back under there. And so this is actually 1 over 2n. Okay? And then the derivative of the n is 1. So if we take the limit of the derivative of the top over the derivative of the bottom, you can see that that does go to 0. So L'Hopital's rule is helpful to us here, and we can fall back on that in this problem. All right, let's see what else here. Problem 16. This is a pretty straightforward problem. You've got 1/2 to the n power, and I think I mentioned in the previous video, if you raise a number that's smaller than 1 or between 0 and 1 to successive powers, it's going to get smaller every time, and so the limit here of a sub n is going to be 0. So these are all convergent. We haven't really come across one that's divergent yet. And actually, I don't think that we will, because there's just two more here, 18 and 20, and these are also, I think, both convergent. All right, let's see here. Problem 18. We've got a sub n, n minus 2 factorial over n factorial. So, talked about factorials in the previous video. Remember, if you've got like 5 factorial, that's 5 times 4 times 3 times 2 times 1. N factorial is n times n minus 1 times n minus 2, dot, 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 all the way down to 3, 2 times 1. So if you think about this here, right, we can rewrite this as n minus 2 factorial over n times n minus 1 times n minus 2 factorial. Right? So that'll cover all the rest of these, and it's going to cancel with what's in the numerator. So this is actually equivalent to 1 over n squared minus n. And if we take the limit of that as n goes to infinity, that will go to 0. All right, let's see what's happening in problem 20. Oh, this is kind of an interesting problem. A sub n, n squared over 2n plus 1 minus n squared over 2n minus 1. Okay. Well, let's see here. It's kind of hard to sort of reason your way into what's going to happen between these two fractions here. It looks like... Now, if we go back to, you know, our rule if we go back to the rule that says that if the power of the variable is higher on the top than it is on the bottom, then when n goes to infinity, this fraction will go to infinity. But so does this one. And when you have infinity minus infinity, that's what's called a non-computable value. You can't, it's an indeterminate value. You can't figure out infinity minus infinity. Okay? So, what do we do? I would make a common denominator here. Okay? I would multiply this by 2n plus 1 over 2n plus 1, and multiply this by 2n minus 1 over 2n minus 1. So now our denominator is going to be 2n plus 1 times 2n minus 1, or 4n squared minus 1. In the numerator, we get n squared times 2n minus 1 minus n squared times 2n plus 1. So that's 2n cubed minus n squared minus 2n cubed minus n squared. So these cancel each other out, and we come out with negative 2n squared over 4n squared minus 1. So now if we want to take the limit as n goes to infinity here, notice the powers are the same, and so this limit should be the ratio of the coefficients. And this is a convergent sequence. Okay. So that's it for this round of handouts. And I believe it's next week we will get into some questions of exactly how far out in the sequence do you have to go to get close to the limit. Okay, which is really, we don't talk about it a whole lot in this class. It's mostly focused on in courses on analysis, which is sort of the underlying ideas of calculus. So this is a little bit of an introduction to analysis, which is actually, even though we don't talk about it, it is a very important subject. So that's why I want to give us a little bit of an introduction to that. So when we do the next video, that's what we'll be talking about. We'll see you then.